Three, two, one. We are live. So, welcome back to another episode. Very excited to join you today. And everyone in the UK is returning from a Queen's Jubilee, which I've heard various different accounts of how fun or how crazy it was, which sounds like a brilliant way to celebrate the Queen, which a lot of people had a lot of fun with. But yeah, Curtis, welcome to the show. Great to have you on, sir.
Thank you.
I'm looking forward to today. We've got some good topics coming up. We want to look at, a few things and what HPC is and what storage is, and look at some examples where we can, and looking at disk performance. So, full transparency, some of these areas are not my speciality, but that's why I wanted to bring you on, because from a very selfish point of view, I get to learn from this as well, and the fact that the audience gets to learn from it is an added benefit. So, yeah. Maybe you can kick us off by giving us a bit of a background on what your origin story is and how you joined your journey as being a software architect at Panasas. Is that right? Am I saying that correctly?
Yep, Panasas. Yeah.
Over to you, sir.
Sure. So, software architect. I wrote my first line of software about 46 years ago now. I've been doing storage-related things for the last 37 years.
Yeah.
So yeah, I don't look it, but I'm old. So there's a couple different things about history that help us with today, right? There's back then there were, I don't know, call it 8 or 10 major system vendors, and everyone had their own operating system, and every operating system had their own file system. And whereas today there's iOS and Android on phones, there's Windows for productivity, and Linux owns everything else.
Yeah.
So a very different environment back then than there is today. So there was a lot of need for storage engineers back then, people who created file systems.
Yeah.
Today, less so. It's still an interesting project. I enjoy it because it's just a cool thing to do. But so me personally, to go back to that, and then we'll talk more about the history of it. In 1990, I started at a company called SGI. They were the NVIDIA of their day. NVIDIA, in fact, was founded by a bunch of, well, I shouldn't say founded, but early employees were a bunch of ex-SGI people because all high-end graphics. But go ahead.
Yeah, I never knew that. It's cool to see, because you see where you see the strength to what NVIDIA are now, and it's awesome to know that kind of history. I didn't know that, but that's awesome.
The SGI, they built very high-end graphics systems, and NVIDIA was started chewing away at the bottom end of their market because they had a single GPU on a card.
Yeah.
And so NVIDIA, SGI kept going higher and higher, and eventually NVIDIA ate the foundation out from under it, and SGI collapsed. Right, and so that was the cool and sad part of that story. But so SGI, they needed high performance storage to support their high performance graphics. They were also an early entrant into what's now called HPC, so they needed storage. So we built our own file system there. I was one of the first 5 people on the XFS file system. Later on, another group of people ported that out of IRIX and into Linux. So that's still the XFS that you see today.
Yeah. I'm going to just quickly ask Curtis, what is a XFS system? Or
sure. You're on your laptop. If you're running Windows, you'll see folders and files. Those in my terminology would be directories and files, and that's the software that creates that out of a flash drive or a hard drive is called a file system.
Got you.
And there's a formal standard for what they do and how they do it. It's called POSIX, POSIX. And we'll talk more in a minute about block devices and how they're different from file systems and that kind of stuff. But XFS is a file system. ext4 is an old standby file system. NTFS is a file system. Let's see. We're going back through the history.
Yeah.
A whole different piece of history, again, informing how things work today, because the topic here is what is HPC and what is storage and how do they interact and how does this relate to AI and all that. So way back in the dawn of time, the 1960s and 70s, Cray built what today we would call scale-up machines. One big machine that was really, really fast and expensive. In the 90s, Cray Incorporated figured out how to do scale out. take a single large computation, a weather forecast, and spread it across hundreds of independent computers all talking to each other over a network.
Cool.
Right. And so that was a software innovation, how to effectively spread a single computation across a bunch of computers.
Yeah.
What that did was it created demand for a lot more data traffic, a lot more bandwidth coming out of storage. And so people took the same scale out methodology and applied it to storage. So
Yeah.
instead of one computer sending data across a network to a bunch of computers, you scaled out your storage, and you could have a bunch of computers sending data to your computers, to your compute nodes. IBM GPFS, General Parallel File System, predated Panasas by just a bit. They have a very different architecture than Panasas. Panasas was the first sort of modern parallel file system, where different, a bunch of computers, all with storage devices, would serve data in parallel to the compute nodes in your compute cluster.
Yeah.
Where to go from there?
I've got loads of questions.
Question. I rambled on to a whole lot of stuff.
No, I'm loving this history lesson because I didn't know. Tell me a bit more, because I didn't know that was how you were saying in the 1970s, right? And that's how they came. What was the system again? The
Cray.
Yeah, exactly. And
Right.
what's that kind of gone into now? Because you said that was like the world's biggest. I think of like a big computer now, and I think of quantum computing. That's what my head just jumps to. Like, that's all I hear about being the next big computer. But is that kind of system still in place? How did that evolve, if I can ask? Or what was the story?
Cray was it was a guy, Seymour Cray, and it was named after him, right? And he built really, really high-end computers. So a single computer, just really big and fast.
Yeah.
And then Cray Incorporated in the 90s did the scale out thing, right?
Yeah.
And that's a lot more effective. So people don't build single monolithic super fast computers anymore. They just build scale out. Now, each node in the scale out is pretty damn powerful today too, right?
Yeah.
Especially if you stuff a bunch of GPUs in there. That's how you get to the exascale.
Yeah.
The sort of the pinnacle of performance is fast individual nodes and thousands of them all lashed together with a network.
Yeah. Where's all this stored then? How does that all work? How does the storage work? How does the storage side to all these thousands of nodes and transferring all the data and all the connectivity between it?
Right. Most environments today, most HPC high performance computing environments today, a little bit more than half are Ethernet connected.
Yeah.
Meaning it's just Ethernet, normal cabling connecting all the different nodes together.
Yeah.
Some of it's really fast, 100 gigabit, etc. But still, it's fast. Ethernet. There's a competing technology called InfiniBand, which is now owned by NVIDIA, and it's about the same speed as Ethernet, maybe just a bit faster, but it focuses on super low latency. So you got two compute nodes, and they're working on pieces of weather, one in New York City and one in Boston, right? That they're doing the weather for each one. And they need to talk to each other. Oh, well, I'm sending some wind your direction. Oh, I'm sending some rain your direction. That low latency is why you use InfiniBand, so they can talk to each other really quickly.
Ah, got you. Didn't know. Right? I didn't know. That's cool.
Yeah. So, and high performance computing isn't just weather. One of my favorite examples is you go to a grocery store and you buy a gallon jug of milk, and it's a plastic container, right?
Yeah.
The consumer products company, they want that makes the jug. They want to minimize the amount of plastic that goes into it because it's expensive, but they want to make sure that if you drop it in the store, it doesn't break.
Protected, yeah.
That is a computational fluid dynamics problem and a structural element problem that they use HPC supercomputers for, to figure out how to minimize the amount of plastic and still keep the strength they need.
Oh, really? That's so cool. I didn't know that was behind it. That's awesome, man. Tell me another. Have you got another example? That's awesome.
I mean, well, it used to be back in the days when pagers, the little pager thing, right?
Oh, yeah.
They had a lot of finite element analysis, structural computation to make sure that when they dropped, they didn't break. I mean, with phones, they the same thing is happening, but it's glass rather than plastic, and so there's some other things involved. But
like is or something that they said they were using. I don't know if that's just a term for it, but I read that whole story on it's a really good book by Warren. So I'm not trying to cut in, but it just reminds me like it's kind of to this, like how they got to the finished product.
Oh yeah.
It was just amazing. Like I think it's in Walter Isaac's book, or maybe it's in another book that I can link, but it just talks about the structure. I'm sure it is, because it talks about Tim Cook going over there and like they've had to like really figure out the logistics to bring the price down to create it. But they also needed a touch screen, but they couldn't figure out the right glass, and the only place that had it was in China. And then they went into like what I guess economies of scale, how much they have to pay to get that product, and they weren't giving it. And it was just this crazy story. It's just like, and you think it's the same kind of thing that I'm thinking about with this.
Oh yeah, the amount of computational power in this compared to the first Cray machine.
Yeah.
The biggest machine you could buy in 1960 is, I don't know, a hundredth of this.
Yeah. That's mad. And they said I don't know if you've seen this, Curtis, but in the next, the glasses that are coming out, they said, or it's rumored, and I reckon they're all coming out with glasses. I don't reckon one's going to be. I reckon, Microsoft are already coming out with not glasses, but with their all VR headsets and the HoloLens, all these different things. But the glasses, I can see two key companies coming out with it, and probably Samsung will eventually come into them, but Google and Apple. And they said like the Apple one will have more computational power going off. I don't know, their route, but going on, they're pretty accurate from the same people that use them. Will have the same amount of computational power as a MacBook Pro or a Mac in glasses with such a small wireframe. I was like, how the fuck is that possible? Like, that's crazy.
Yes. Oh yeah. I mean, the classic example, right? The Jetsons, right? With your or Dick Tracy with his watch.
Yeah.
We're there, right? You can have video conferences on your watch now.
Just call in and just like, hello, how you doing? I just feel weird. I just feel like if someone saw me in the street, just like, oh, I'm just tuning in. Like,
but it's amazing.
Yeah, well, that's cool. And maybe just walk me through them. So when we were talking on that then, so HPC, what does that stand for? It's to do with like storing data, right, and making sure that is that right? What is it?
HPC is just a simple acronym. It's high performance computing.
Yeah.
Now, what high performance computing is the sort of back up. HPC isn't a technology; it's a suite of best practices. It's how you take various pieces of technology and you put them together. It's the best practices that the people who need high performance computing, they've developed over the past 40 years. So when you build out an HPC data center or you're building up an HPC cluster, there's a whole lot of rules of thumb about how you put it together, what technologies you need and how you connect them and how to balance it out so nothing is overpowered and bottlenecked by something else. You get this balanced environment. And that's just experience. People have developed how to do these things. There isn't really any hard rules about how to do it. It's just experience.
Yeah.
And so, right, high performance computing, there's three major components. There's the compute nodes, which you can have 20 to 20,000 computers. There's no upper limit, right?
Yeah.
All connected with networks. There's the networks proper, Ethernet or InfiniBand, and how you connect them matters. Like, normally you put a top of rack Ethernet switch and you connect everything in the rack to that switch, and that has high bandwidth links out to a core switch and that kind of stuff. That's great, except in an HPC environment, best practices are you create a torus, a donut shape, or you create a butterfly, or there's these names for different network topologies, how you connect them. And that will have an impact on how effectively you can use the compute given a particular set of jobs. So networking isn't just, throw some cables in there in an HPC environment. There's a lot more tech to it than that.
Sounds like just quickly how they come up with a car, how to make it more streamlined. Like you can come up with a pattern, make it more connected, right?
Oh, yeah. Right. Yeah. And then the third leg of the stool is storage, right? You have to store the data. And if you've got a significant sized compute cluster, then you need a lot of bandwidth to move the data from the storage so they can compute on the data, and then move the results back. So you're constantly moving data back and forth.
Yeah.
The purpose of this, what the customer wants out of this, is a particular end output. They want a phone design. They want a milk jug. They want whatever, right? And so the compute is where people start, and they say, well, I know I need a lot of compute. And I say, well, I have to connect them. And the I have to carefully design my network. The very last thing you think about, unfortunately, is storage, right?
Yeah.
I geek out on storage because I like it, but at the same time, storage is clearly a means to an end. You don't buy
Yeah.
storage because you like storage. You buy storage because you have stuff you need to store,
Yeah, that's such a good
right?
point. I never thought about that. I've always bought storage because I'm just like, I run out of storage. It's not like, oh, I know what I'll do. I'll get the storage a year in
Yeah,
advance so I can get it at a discount. It's always like, I need it now, so I'll buy it now. It's very instant. That's a great point, Curtis.
yeah. There's a certain amount of ego involved in buying, a big compute cluster. So, I got all these computers. It's great, but you don't get that for storage. Like, yeah, I get so smart. No, don't
Yeah.
get that about storage. But um, but at the same time, the storage is important because if you don't have fast storage, then your computers are going to be idle waiting for your storage.
Yeah.
So
So
accurately sizing it and getting the right there's a concept called workload that we use in storage land where um, a weather simulation is going to do read and writes of files in a particular pattern. A
yeah.
computational fluid dynamics thing, like your milk jug example, is going to do them in a different pattern. AI is going to be doing IO in a different pattern. We call that a workload,
Yeah.
the different patterns.
Yeah.
And different storage systems are optimized for one workload or another workload or a third one.
Yeah.
Um, or they're better at them or not good.
Yeah.
Like you would never use a parallel file system that was built for an HPC environment. You'd never use that to support a database,
Got you. How many
right?
patterns have you come up with, Curtis? Or how many patterns are there?
Well, Panasas only has a relatively small amount because at the beginning, the company, when they were developing the technology, they sort of gave everything away. If you've
Right.
heard of parallel NFS, PNFS, we
I have
gave
it.
that away.
Yeah.
There's a long story behind that, but so we've got some really core key patents, but um, because we've been in business for 23 years now, I think 23. Everybody knows our architecture, and they take our architecture and they build off of it, and they
That's
create their own architecture that takes the best of ours, and it's something new they want to try, and they go with that.
I love that. I'm
Yeah.
such a big fan of being open source and like making sharing is
Oh,
caring and making sure if someone else can do it better. But I always think, well, if they
yeah.
can do it as well, they might become a customer or they might open a doorway for me or whatever it is. And I just think holding it
Yeah.
back. So just quickly,
Yeah.
love that point that you're doing that, Curtis, with Panasas.
Yeah.
Yeah.
Um, so um, a traditional HPC parallel file system like Panasas
Yeah.
is really good at very large files,
Yeah.
sequentially reading very large files like terabyte size files. Um, there's no upper, and it's good at small files, but that's not why you buy a parallel file system.
Right.
Is for small files, right? In an HPC cluster these days, most clusters are good sized and expensive. A couple of hundred nodes to a couple of thousand compute
Yeah.
nodes, and the customer wants to keep that as busy as they possibly can.
Yeah.
So they will put their milk jug simulation on there, and they'll put a bottle for hair shampoo, and they'll put a bottle for other things. All those jobs on there at the same time. They'll also be exploring neural networks, AI technology, trying to figure out, well, can that benefit me, right?
Yeah.
They'll also be doing a whole lot of other things, injection molding if they're really working with plastic. And so you get the cluster that's running not just one job, but
Yeah.
a whole lot of them, each with their own workload. And so what comes to the storage is a combination, a mashup of all of those workloads. So today, a modern parallel file system from an HPC environment has to be almost a jack of all trades
Yeah.
because they've got everything coming in. Life sciences stuff may be mixed in with weather simulation, all sorts of things.
How do they just quickly? How do they decide or get through that? How do they do? Do you need to do that, or can when it's fed back? How does that part work? If it's all coming back, because I'm thinking here, Curtis. So it's like a not a decision tree, but like there's loads of different angles, and then off that you've got nodes, and off that you've got all its workloads, and the workflows might be
Right.
like 5 workflows, and then it's all
Right.
coming back into one route, and it's trying to make sense of
Yeah.
it all, trying to collaborate. How does that work?
So people talk about objects a
Yeah,
lot, and we can talk more about objects in a minute, but
yeah,
HPC is file systems. There's
yeah,
not all that much in the way of object accesses from HPC jobs. They use files and directories. So from the point of view of a storage product like Panasas, we present a file system And the applications will just open, close, read, write, do all the things they normally do.
Yeah.
It's just that we have to make it fast. That's our problem, is to make it fast.
Yeah.
And so the challenge for a file system of any stripe, of any kind, is you've got a POSIX layer on top. This is files and directories, and the application does what it wants to do. At the bottom, you have commodity storage devices, hard drives, flash drives, things like that.
Yeah.
And in between is a whole lot of your architecture. How you make use of those commodity drives that everyone uses. There's no special drives out there for somebody, right? They all have to use the same devices. In between is your architecture and how effectively you can use those devices.
Got you. How big have you seen it before? You said with the amount of nodes, if a good one's like a couple of hundred to a couple of thousand, have you seen one where they're like 50,000 or something? They've just gone over.
Oh yeah.
Why would that happen? Why would that be possible? A lot of questions. Sorry.
Oh no, that's fine. We used to have a very large silicon provider as one of our customers, and they were pushing up to 30,000 nodes, doing a single what's called tape out, where all the nodes would take the silicon design mask, and they would merge it all and get everything perfect, and then generate the final image that would be used in the masking for creating the silicon. So it's this whole process called tape out. It's part of electronic design automation, EDA. And so they had 30,000. Now they wanted to push toward 100,000 nodes simultaneously, and we said, okay, fine. You go build your own custom device, custom environment for that. We don't want to deal with. I shouldn't say don't want to. But having one big customer that dominates your business is not as comfortable for a commercial enterprise as having a lot of customers that all have, they're all doing business, but not just one big one.
Yeah.
So
I think that's a good way of looking at it. And so I've got a note here about parallel write file systems. What are they? Right. How do they work? What's maybe set a scene, or in a business or consumer application? How do they work?
Sure. So you've got your application running on a compute node, and it wants to open a file. So in the traditional architecture, and our file system is called Panasas. In Panasas in particular, you'll say open a file named foo, and that will come to a director node, a metadata processing node. In Panasas, there are metadata processing nodes and data storage nodes, two different classes. They're running different software in them, but they all cooperate to make Panasas. So you say, I want to open that, and the compute node sends that message to a director node. The director node says, oh, I know where that is because I've got access to a whole bunch of data, information, and it sends back a map. The compute node then says, oh, I know where to find the pieces of foo. It's a really large file, and it lives on these 12 nodes, these storage nodes. And then I'm going to read in parallel from those 12 nodes. And that's why it's called a parallel file system. And that's why it's fast, is because you're not bottlenecked on one node delivering data. You can go to 12, you can go to 20 nodes, all feeding you data in parallel, 20 times as fast. So
that's awesome.
And when you're doing a write, the opposite direction, except for when you're doing a write, we use erasure coding. So the compute node will say, I want to write this, a 20 gigabyte file, and I'm going to stripe my data across these 12 nodes, but I'm also going to include 2 extra nodes for erasure coding information. And so that's the reason it's reliable, is because with erasure coding, you could have one node burst into flames and you wouldn't lose any data. You could have 2 nodes burst into flame and you still wouldn't lose any data. So
you can just keep running and keep parallels, like a backup almost, and it can keep relaying. That's cool. I feel like businesses might actually get some good operational advice from this, because the words like bottlenecking and how to group it all and how to make sure things run simultaneously, it's a big problem companies here. I don't know if you've seen anything with it, Curtis, but when they try and do these big digital transformation shifts, I read 85% fail or something, and it's just it is these sort of problems that pop up, not from the technical side, but from an operational side, right?
Yes. Yeah. That's why I like the description of HPC as a set of best practices, rather
Yeah.
than a technology, right? Because it's, oh, this is a path that a lot of people have walked down, and this one works. Over here, you might be fighting your way through the brush and fall into a hole, but this works.
Yeah, because it needs to, right? It needs to
Yeah,
like it's not like you're dealing with team members, and it's not like you're dealing with people with which I'll openly say have different personalities or different ways of doing
sure.
things. It's a computer and it works to a fixed flow. I feel like that
Mhm.
might be one of my books. I'll put it. Oh, I don't know if how far I'll be able to write about it. Maybe that's a book
Okay.
to write, like operational excellence discussed by data nodes and HPC and
Yeah.
everything. That's cool. I like it.
One more thing about that I think is important or relevant to your audience.
Yeah,
The skill set of knowing the best practices,
yeah,
the suite of people that know that, the engineers, the operational specialists, is shrinking because
yeah,
HPC isn't as popular as Web 2.0.
yeah,
And as all those people, practitioners, start to retire, then it will become even harder and more expensive than it is today to find those specialists that know that.
yeah.
So people, hiring the right people, and so that they can work your way through the forest and give you a system that's working reliably and at high performance. Uh, People in HR and compensation packages, all of that's actually part of the equation because
Yeah.
of the shortage of HPC specialists.
Yeah. So do you reckon there's any other reason to a shortage, or do you think it's just, or what is it about Web 2.0 that people like to use, do you think, Curtis? Or
Oh,
what?
HPC isn't one of these. It doesn't run here,
Yeah.
right? HPC operates traditionally in way
Ah,
behind the scenes in a
yeah, yeah.
glass house,
Oh,
and it's boring,
yeah.
right?
Storage.
Now, if you're interested in extreme scale or high performance, then it's interesting. But most of the new graduates are interested in their phone is already implanted in their head, so they just use their phone for everything.
Yeah. And I guess they're getting more trained on things like AWS and like using
Oh yeah,
all, would that be right? Like using it for like a
yeah.
cloud infrastructure instead, which obviously poses a lot more security risks, but or arguably poses more security risks. I don't know fully, but that's what the argument I always hear. But yeah, everyone moving over to AWS. Yeah.
The HPC traditionally was way in the background. There was
Yeah.
a corporation, because we're talking corporations here rather than labs, national labs, or even universities. But a corporation, if you take them as an example, they had their business processing sort of in the middle of the corporation, and HPC was way out on an island.
Yeah.
Um, the value of HPC, because that's where most of the AI is done now
Yeah.
in AI, is in HPC technology base. Let me back up. So HPC is a suite of best practices. AI appeared, and you want to use more than one GPU,
Yeah.
more than one silicon accelerator. So then you can, oh, well, I can put 8 in a computer. Okay, well, that's not enough. So
Yeah.
now you're talking scale out, and HPC that's best practices for scale out.
Yeah.
So AI at scale becomes HPC. And what that means is the businesses, the enterprises are going to drag HPC into the center,
Yeah.
become part of the core of your corporation IT environment.
Yeah.
That's going to bring a whole pile of security requirements to HPC that have not been present up to this point,
Yeah.
because now it is the part of the crown jewels, and you need to protect the data that's there, as
Yeah.
well as the ability to compute. So
Yeah.
ransomware, all those things become relevant for HPC now, where they weren't 5 years ago.
Yeah. And where does that lie then? So, and if we can go into this and just tell me to
Sure.
stop at any point, if not, but with the security, like, how does that differ from what it is now? Because I remember quickly, and I don't know if this is the right point, Curtis, but I worked at Sogeti. So Sogeti were a
Sure.
subsidiary, they still are a subsidiary of Capgemini. And I remember there was like computer storage rooms, that was like restricted access, and you couldn't do it.
Hmm.
And
Hmm.
I thought it was always a bit crazy because you're in the middle of the city with 7 million people around you, or how many are in London, 6 million people,
Right.
and you've got some very high secures, and it's like
Yes.
this isn't like the government's like security council or something, and even that's being treated as like passcode only, like only required
Right.
entry.
Right.
How's that changing with security to what you're saying now? I don't know if that example
Oh
makes
no, absolutely. That's
sense.
so physical access security is important, because if you have physical access, you can break any type of security.
Yeah,
But physical access is not how North Korea makes $6 billion a year, right? It's all online hacking. And so
yeah,
online security, that's why you hear the phrase zero trust.
yeah,
That's the next big architectural push in security, is don't just have a firewall around the outside edge, because if somebody makes it through the firewall, then they've got all of that good chocolate that they can suck up, right? So you have to have an environment that is, uh, I won't go too deep into zero trust, but where everything is validated, every single operation to and from storage over a network, it's all validated with cryptography. So, yeah, online hacking is very different from physical security. Can I steal a hard drive with data on it? If you leave your laptop in a taxi, can I get to the data on that? Those are an entirely different class than online hacking.
Yeah. Did you follow the story? I feel like you likely would have, but this is reminding me of something I want to ask you. Did you follow the story of Edward Snowden and whatever? I'm pretty hard not to follow it, but
yes.
in your kind of field of interest. But how mad did you follow that, Curtis? Like I watched the film and I read the book and I watched his interviews and stuff, and I think he walked in like anyone else with a little hard drive, plugged it in, and walked out. I was just like, that's a level of security for a national security center. It's just like we're pretty like, and that's a personal opinion, but it kind of made me just think, like,
there's a in that case there was a whole lot of operational failures on the security teams that were managing the data. But there's in hacking world they have a name for manipulating someone into doing something called social engineering. So if you want to break into the AI journal, for example, they would drop a thumb drive next to your car. And you go, oh, look at that. I wonder what's on that. And you plug it into your computer.
Oh, my God.
Right. That's a social engineering thing. That's not a technology. Right.
Yeah. I'm never picking up anything next to my car now.
Yeah, that's good plan. Good plan. Yes.
Well, thank you for that, because maybe I'll just mysteriously see one appear and I'll just boot it as hard as I can. Like, stay away from me.
Take that thumb drive. You want to know what's in it? Plug it into somebody else's laptop.
See what you can do for there. Yeah, but do you think like certain technologies, Curtis, like blockchain, what's your kind of view on? Do you think it has anything to do with it, or do you reckon it's going to change the shape of, like you said, it being less popular? I'm talking from the HPC kind of standard. Have you got what views you got on that coming through?
I think it is going to have an impact. See, there are people who really want to use blockchain to create currencies that aren't under the control of a government.
Yeah.
And that last bit of aren't under the control of a government, that's a political question I don't want to get into, right?
Yeah, cool.
That creating currencies, okay, fine. Blockchains in terms of provable change of ownership, prove that the transaction happened, that kind of thing. Those are interesting. They're also secure.
Yeah.
Right, because they're based on the same cryptographic techniques that a lot of other things are, right? And just leave it at that. There's relationships there.
Yeah.
And so I think that there is a role for that in the future. Yes. It also has the convenient side effect of requiring a whole lot of compute.
Yeah. Yeah, you need big capacity computers to be able to power them. Like, it's like how much power it takes to mine Bitcoin or something ridiculous. I can imagine. And I don't want to go in that conversation with Bitcoin. I don't really understand it, and it's not an area I'm passionate about. But I always think, like, if that's the kind of energy it takes, it's just like, whew, I'm sure. It's always on people's agenda. And I think it's quite cool, like how like I always look at blockchain, Curtis, from a different point of view, like how people can get married on the blockchain. I've got blockchain. I got gifted an NFT through it, and by Steve, who was very kind of him to gift it me. And it's just kind of cool to see how it can work from the classic level of everyone jumping to Bitcoin. I'm just like, it's going to be such a. You see these people making thousands and thousands, but then it always makes you wonder, like, how secure actually is it? Because I don't know, Curtis. You maybe in your previous years, like how could you even idea, or could you even kind of form in your head the idea blockchain would even be about 10 years ago or 20 years ago? Like, I think, what's the next technology, right?
Yeah, like neural networks. People understood that there might be some possibility there that they had value 20, 30 years ago. But it wasn't until like 10 or 15 years ago that the computation could keep up with doing a neural network, that they actually was practical to do to build one. And now things are taking off, and it's a self-reinforcing cycle that a GPU has enough computational capability to do a good-sized neural network.
Yeah.
And because there's so much value there in natural language processing, voice recognition,
Yeah.
dictation, then NVIDIA builds the next generation and you keep going upward, right? Or Google builds their tensor cores or whatever.
Yeah. Yeah. Or Intel
So
come out with something brand new, or like some sort of
mhm.
display or some sort of
Huge competition.
yeah. Yeah. Well, I always love it. I always love going to GTC because I'm always just blown away by what they're coming up to. Like, and
Oh yeah.
not always, but like, there's always some sort of like tech there that maybe like, and they partner with, or there's something that I've never thought of before. And that's why I love this space, because I always think, how much do we actually know, Curtis? Like, it's always rapid innovation that we can't keep up with. I love it.
Yeah.
And what do you think then? Sorry, were you going to say something?
Oh no.
What do you think of like so like you were mentioning it as well, so you can have storage and then like, so for example, I was storing too much stuff on my laptop and the laptop started to slow down and it started to close on me and it started to malfunction, and fair enough, I had to delete a lot of files, or I had to find a way to back up. As your example said, I didn't buy storage and I needed it. What do you think the difference is for, or why storage over disk performance? What's your views on that, or any examples of why companies might use it?
Okay, so a joke. Hard drives and flash drives, they're binary devices. They're either new or full.
Yeah, that's so true. I love this. I'm learning. Yeah, these are brilliant ways of looking at it.
Storage geek jokes. Sorry.
Yeah.
So there's a range of different types of storage drives. So you can buy a hard drive, a small one, a large one, but they're basically steampunk devices. They're mechanical. They're fundamentally analog at the base, and little heads moving back and forth across spinning things. Right? You expect to see steam coming out of them. Now they're actually high performance as long as you apply a workload to them that they can deal with. The seek time of moving from one place on the drive to another dominates the performance. So if you do a seek and a small transfer, you get very low performance in aggregate out of them. But if you seek and then do a large transfer, you get good performance, a lot of data per second. And so that's what Panasas does, is we manage how these hard drives are used in our products. Flash drive, in order to only put large files on those hard drives. Flash drives don't have seek times. They're electronic. They're digital. But they have problems, challenges. One of them is called wear out, where any given little piece of silicon you can write to it about 1,000 times, depending on what technology it is. And so the flash drives are measured in drive writes per day. So if it's a terabyte drive, I could write a terabyte per day for the life of that thing, 5 years, and it wouldn't wear out. But if I wrote 2 terabytes a day, it would only last half of its stated lifetime. Right. And so there's this, with hard drives, you have to worry about transfer sizes and locality. With flash drives, you have to worry about total bandwidth. Some flash drives are optimized for very low latency and small transfers. Others are more capacity optimized. They're cheaper. They don't do as many IOPS, but they do good bandwidth. And there are other things there's SATA typical for hard drives, some flash drives. NVMe and NVMe over fabrics are hot buzzwords today. Those are they're a different way to talk to the drive. SATA versus SAS versus NVMe, or NVMe over fabrics. But all of those are what's called a block interface. Meaning that like a hard drive, it's the first sector 0 through sector N. And you can read them one at a time, you can write them one at a time, or you can read them in contiguous groups, or write them in contiguous groups, right? So, but there's no files, there's no directories. The job of a file system is to create directories and files out of those block devices.
So kind of like predicting what would be in that file and where it belongs and where it should be grouped, right?
Yeah, you say, oh, well, somebody wants to create a file foo with 20 kilobytes in. The file system is going to say, oh, I'm going to put it on that flash drive, and I'm going to use these blocks to store it, and I'm going to record that that's where it is in some metadata that the file system keeps on the flash drive. So you want to go read that back. Say, oh, well, foo, I'm going to find the metadata for foo, pull it up, and say, oh, foo lives on those blocks over there, so I'm going to go get it and return it to you.
That's crazy. Yeah.
It's a huge data management problem. When you've got, see, in a parallel file system, there's no upper limit in capacity or size. There simply is no limit. You want more bandwidth, you add more hardware,
Yeah.
right? So we had a conversation a couple of years ago with a company that was going to do self-driving car technology for one of the European manufacturers.
Yeah.
And they were going to need 175 petabytes of data, all told, 175,000 terabytes. And they wanted to retrain their neural network model once every 100 hours. So that was 450 gigabytes a second.
That's hard to even
on a continuous basis, forever. They wanted to do that every 100 hours.
Yeah.
And imagine that they said, well, that's not fast enough. I need my pace of innovation to go faster. So I'm going to buy more GPUs, and I want it every 50 hours.
Yeah.
So that'd be, a terabyte a second.
Yeah.
Right. That's at the upper end compared to most people, obviously. On the other hand, an HPC parallel file system can do that.
Yeah.
Right.
So that's, if I was looking at it, I'd think, well, why can't it do it? Oh, I don't know if that's how I'd look at it, but I can imagine people do look at it like that. Well, we know it's possible. Like, why can't it do it? So you don't think about the logistics. Yeah. It's like when you think how fast a car can go on the road, but you don't want to go that fast because you pose a lot of risks, a lot of threats.
Yeah, high likelihood of dying. Yes.
Well, that's crazy. And I guess how does that affect the downtime then? Is there downtime, or does that hit something, or how does that all work, Curtis?
Well, right. The just in general, as a theoretical thing, the bigger and more complex a system is, the more parts there are, the higher likelihood that you'll have a part fail at any given instant.
Yeah.
Or two or three. And the higher likelihood of it, the system being down, and the higher likelihood of data loss.
Yeah.
So if you start with the basics of RAID, redundant array of independent disks, the founder of Panasas, Garth Gibson, was one of the co-authors of the original RAID paper.
Nice.
So, yeah.
I want to read that. You got a link to it where I can get it from?
Actually, no, I don't have a link to it, but Google it, right? RAID.
Yeah.
So the key to RAID and erasure coding is not, I need 17. I need to be able to survive 17 simultaneous failures.
Yeah.
That might be important, but not for many people. It's how quickly you can go from something's failed to now I'm back to full data protection levels. How can I reconstruct? How can I rebuild the data protection that I have in my storage subsystem?
Yeah.
So in a traditional RAID array where you've got, say, 8 hard drives and one fails, the reconstruction speed is limited by the ability to write to that one hard drive.
Yeah.
You can't go faster than the one hard drive when you're rebuilding. You put a hot spare in there, right? HPC parallel file systems, they don't do that. If one of those, you've got 500 storage nodes, one node crashes and burns.
Yeah.
Then all 499 other storage nodes can collaboratively rebuild that one storage node 500 times faster than one node can do it itself. And so you have a failure, and then 2 hours later, you've reconstructed everything. You're back to full protection level. So then you can take another failure, and 2 hours later, you're back to full protection levels. And it's that recovery time that leads to reliability. And so a parallel file system done well, like Panasas, it gets more reliable as it gets bigger, rather than getting less reliable, which is the traditional answer.
Yeah. Reminds me of like machine learning. It gets better as it learns more mistakes. And I heard some machine learning engineer say to me, and he was like, yeah. And I was like, oh, but how do you get over the mistakes? He's like, I look for the mistakes. He's like, I want the mistakes because I want my model to learn from it as quickly as possible. He's just like, if I can learn from everyone else's mistakes, I have the strongest machine. It was something, I'm paraphrasing, but it was something along those lines. And I was just like, oh, right, well, that's it sounds expensive, but it sounds like a very good long-term plan because you'll have a good, you'll have every mistake possible in your algorithm or in your learning model.
Right. You don't learn from success.
Exactly. Yeah.
You learn from mistakes.
Yeah. It's what pretty much anyone that people like me and you and everyone that, or a lot of people I know that are successful, they've all got that kind of mindset of thinking, well, that's where your biggest lessons come from. And when it hits me again, I know how to handle it. That's cool.
Right.
And it's good to see that's even the process with technology, right? Like that's how technology learns as well, which I think is good.
Mm-hmm.
So I've got a few more questions. I'm conscious of your
Sure.
time. I'm really enjoying this. This is way
Good.
I don't know, I'm really happy we've done this. But looking at it from how you were touching on it earlier, Curtis, how is the HPC industry? Just give me a bit more of a rundown of the audience, a bit more rundown. How is the HPC industry becoming aligned with AI and what we just mentioned there, ML, and making sure maybe from a consumer or a business point of view, what kind of implications that has? How's it coming aligned, and then what kind of implications?
Sure. So, from our experience, like at least most of our customers, way more than half of our customers, are doing some AI already.
Yeah.
Without having bought any special AI storage gear. They buy some nodes that have GPUs in them or some silicon accelerator, and they start playing with it, trying to understand how can I use this technology to benefit my organization and my organization's mission. Right.
Yeah.
And then, so we make a distinction between we're experimenting, and then we're going to now, we found something that's really cool, and now we're going to go into production.
Yeah.
And production is different than experimentation. The data that you need is probably a lot larger, right? You'll toy with something, figure out if it works, and it's okay. Now I need a lot of data to increase the accuracy of the model, or just to get value out of it.
Yeah.
Point of sale terminal information in a retailer is really, really tiny for each one.
Yeah.
But if you're talking a large retailer in bulk, that's an enormous amount of data.
Yeah.
Right? And so one of the things that HPC people don't realize, but I think AI ML people do, is the data is the gold.
Yeah.
Right. That you never throw away any data. More data is better. And you'll always be constantly accumulating data. And every training run, you use essentially all of the data. If you're in production, right? You want to train your model the best you can. And so you use all of it. So there's no such thing as cold data in AI.
Yeah.
And a lot of HPC practitioners are used to the idea, oh, well, I've got a couple of hot projects and the rest of it can go on some cooler storage.
Yeah.
But not so much in AI, because if the project is active, all the data needs to be hot.
Yeah.
So that's one of the surprising things. Panasas, we just recently got involved in an organization called ML Commons. They produce the ML Perf benchmarks, right? And so have you heard of them?
No, I haven't. I need to check them out.
Yeah. Okay, good. I'm glad I mentioned it, right? I'm not an official representative. There's a working group that I'll tell you about in a second. I'm one of the co-chairs on that working group. So,
awesome.
But I believe the goal for the organization is just to help the AI ML community. And so they're doing a lot of different things. They started off with benchmarks for who has the best accelerator technology in their phone. Who has the best accelerator for recommender systems. What's the best architecture for that versus image recognition versus natural language processing, right?
Yeah.
So those things, they started there. They're starting into what they don't call it this, but I call it curated data sets.
Yeah.
Rather than having a data set that is just a bunch of English words and, annotations saying which word it is, right? A training data set.
Yeah.
They want more languages, because that will help the overall community. So they're curating these data sets.
Yeah.
In the long term, it seems to me that everybody talks about bias. Panasas, we went to a conference in Montreal a couple of weeks ago that was all about the ethics and the bias and the fairness of AI and ML. So it was a whole bunch of government organizations and large corporations that wanted to make sure they were doing right by their customers rather than implicit bias, right?
Oh, that's cool.
So it is. And so implicit bias generally comes from the data set.
Yeah.
If 90% of your data is spoken English, then somebody comes along in speaking Swahili or Spanish, they're not going to have such a good experience.
Yeah.
Right. So that's what I think the opportunity is for a curated data set. You include those other languages and you massage the data, get rid of the bias that's in the data.
Yeah, language barriers is so important, isn't it?
Right.
Just quickly on that point, Curtis, I want to expand on it, anything you were going to say. But when I went abroad, tell you a funny story. Basically, we were in an Airbnb. A piece
Right.
of my clothing fell off and it went down the apartments and it fell in someone's back garden or backyard.
Oh,
And we had Croatia while we were interrailing. This was years ago. And even at that point, I said maybe 4 years ago, something like that. And I was going down the stair and we came to this delightful old lady, but she didn't have a clue how to speak English. So before I could even think, I was just like, right, whipped out my phone, Google search, and was just like open translator and was just like, and we were just going back and forth. And I was like, and just like, just goes off and chases it. And I was like, that's the importance of communication, right? Like, it's,
Oh, yeah.
as you're saying, to this situation.
Yeah. Yeah.
But I'd have been screwed about that, but yeah.
So how I'm involved, the purpose of the benchmarks that they have today are things like, if I want to get a particular accuracy level and a particular time duration, I need this many accelerators.
Yeah.
I say accelerators because there are new companies coming along building silicon, not just GPUs from NVIDIA, right?
Yeah.
And so the benchmarks are intended to help people size their compute environment, and then the networking. And the new working group that I'm involved in, I'm a storage guy, right? Is the storage working group. Say, well, how do I size my storage for a given size of compute? Do I want more storage or less? I don't want to. If I have too much, I've paid too much because I'm not using it. If I have too little, I'm bottlenecked.
Yeah.
Right. So that's what the storage working group is doing.
Yeah. That's awesome. I need to check them out. Sounds like a good job that they're doing. Yeah. And I think, if you look at it from that point of view, like, what was I going to say? I was looking at how, just quickly there, and I was looking at the earliest industries recorded for using data, because what you said really intrigued me. And apparently, it was first used in 1880, where it was done very manually and it was recorded and it was looked through they classed it as data to actually look at kind of storage as a whole thing. I haven't read the full article, but 1880 apparently is the earliest recorded use of data. That's wild. Like, to think where it's going to now, right?
Yeah. Charles Babbage.
Maybe. I don't know. It's just seeing it there where it's
if you get a chance to watch The Imitation Game.
Yeah, I've seen
that's a great movie. And it's not just the acting and the storyline as well, but the first modern digital computer is what he was building. Alan Turing built. And that's why it's called the Turing Challenge and the Turing Test and the Turing Award, because, so anyway, it's cool.
Yeah, no, he's a pioneer. I love that guy because you watch the film, and then I haven't read any books about him, but I've read some kind of articles and I've read research papers that kind of mention what he was building and how he was building it. And obviously in the film, you can see it all fictionalized, or I'm sure it's largely correct, but you can see how he's really being challenged to people saying, you're looping your head, this isn't going to work.
Yes.
And then they obviously have that scene where they stop something happening. For anyone that hasn't seen it, I don't want to ruin it, but it's quite an intense scene and it brings it all forward. You're just like, that's at the forefront of like really game-changing stuff, man. Like, that's really cool.
It is.
And I think that's quite cool that's quite a good way to just wrap up where I want to see you or get your feedback, Curtis, on where you see this going. So you just spoke on how AI and ML and HPC are going to come together and how it's really over-fueling each other. I feel like I could ask you 1,000 more questions. I'm sure we'll get the chance to do it hopefully in person. But where do you see the future of the industry going, or HPC? And you mentioned it at the start, people are moving away from it. Was it an educational challenge, or what advice would you? I've got a lot of questions, so you can pick it from one or two. Where do you see it going, and then what maybe advice would you give to people investing in this area?
So if we take a person, a CIO, for example, who's saying, okay, AI sounds cool. I think I need some of that. I don't know what it is yet. I don't know how it can affect how best to use that technology for my organization. There's a learning curve. Just, what are the basics? There is finding the data scientists that will help you actually do the work. There's all the hardware support you need, the compute nodes with the GPUs or accelerators, networking and storage. All those things ends up being a really large set of problems that aren't the same. It's not an Oracle database. That's cookie cutter stuff. You could do it in the cloud, but you're going to pay a lot more. Right. Partly because it's hot, partly a hot topic, partly because the accelerator is expensive, partly because clouds are not built for HPC. They're built for commercial processing. Look at it this way: a cloud, you rent an EC2 instance. Well,
Yeah.
that physical piece of hardware is probably running 4 or 5 EC2 instances at the same time. They're
Yeah.
depending on the workload being bursty, and that's
Right.
where they make their money. Well, they're going to lease the node to you to 5 different people all at the same time. VMware does the same thing,
Yeah.
right? HPC is not like that. HPC wants 100% of the computer for a week,
Yeah.
and so it doesn't fit well with the cloud design. Now they'll get there eventually, but at the moment you'll pay like 7 times as much to run an HPC job in the cloud as you would on-prem.
Yeah.
On the other hand, if you need the job done, you're going to pay the money and you're going to get it done.
Yeah. Yeah. That's cool. Like I didn't realize that. Yeah. Basically, like it's like buying versus renting. It's kind of what I'm seeing, like that kind of analogy. Would that be right or not quite?
Yeah, buying versus renting, but also taking a bus versus taking your own car or
Yeah.
taking a sports car.
So like one up.
Right? You taking your own car, you could go 60 miles an hour. In a bus, you're going to go 40. In a sports car, you go 100.
Yeah.
And but the prices are different too.
Yeah.
Right. So there's the price value, reward, cost, reward, all that stuff.
Yeah. Cool.
Other things that another major change that's happening, that as HPC is pulled toward the center of an organization that needs to get something done, and storage being a means to an end, not an end in itself.
Yeah.
It used to be that the HPC people thought, oh, well, I need the fastest storage possible, and I'll hire a group of 6 people, and they will keep that thing fast.
Yeah.
Not understanding that the headcount cost, the 6 people for 5 years is like $3 million once you put all the costs together.
And
that's
hard
on top
right?
of
And training. Sorry.
Yeah,
exactly. Sorry.
Right. No, that talked to a university over in UK a couple of years ago, and they lost the head of their storage group for their HPC cluster. It took them a year to find somebody who was qualified to do that, to take that role.
Yeah.
And so the cost, the people shortage, just the headcount cost is driving the industry to look more closely at, can I have a reliable high performance storage system? And that's what Panasas does. We saw this trend quite a while ago, and we've invested to make sure it's a reliable product, more of an enterprise class than it still has HPC performance, but it's enterprise class in terms of reliability and manageability and all that. So that's another change that's happening, that if you move to the center of an enterprise, the enterprise is going to have expectations that are different from what used to be for the HPC world, not just security, but reliability, all that stuff. So that's under a macro trend going.
That's cool. Do you reckon there's any micro trends going, or anything smaller, or that we haven't discussed yet? I know we discussed a few. Any other ones?
Yeah,
stop yet?
Little buzzwords like NVMe over fabrics. 10 million IOPS. And it's like, well, 10 million IOPS is really important if you're running Oracle.
Yeah.
It's not relevant if you're running files.
Yeah.
Right? It's because it's 10 million separate random 4 kilobyte reads and writes. That's not file systems. That's, a database.
Yeah.
And so there's lots of hot topics, objects. How many years now, how many decades of people saying, oh, tape is dead.
Yeah.
The tape market is now larger than it was 10 years ago.
Yeah, it's like kind of rebound because it's more precious.
Right.
I don't know the word for it, but more like, unique.
And the like Vast is claiming, they're another HPC company. They're claiming, oh, we're going to kill the hard drive. No, you're not. You're going to provide an alternative, but very few technologies actually die.
Yeah.
Right. And so you'll be adding things. Let me back up. So anyway, just the macro trends. People are always claiming that, oh, this technology is going to die, but it probably won't. It has a niche. It'll find the niche, and it'll be valuable in that niche. It's optimized for that. Tape is zero cost, no power, no carbon footprint, no cost when it's not in a tape drive.
Yeah.
Right. And so if you have long-term storage needs, backups, or just a project you want to archive for 10 years and then read it back again, tape is perfect.
Yeah.
Right. So knowing what technology to fit what need is it is important. It used to be that there was only one technology, that was what you used. Now there's a choice, and you have to pick the right one.
Yeah.
So
I think that's a great trend because I look at it from maybe I love how I'm using examples to try and like get my head around because this is some cool. I've honestly learned a lot, Curtis. But I think of my brother that he loves vinyls, and that stuff can be expensive, man. I look at it and just invest in like a Sonos speaker or a nice speaker or whatever it may, an Amazon Echo, whatever it might be, and subscribe to either YouTube Premium or Spotify for what, like £10-15 a month when you go to. And he's just like, no, like this, and like that can set you back like 40 quid just getting one vinyl, if not much more. Like these are just for like standard replicated ones. If you get for like unique, you can talk hundreds, thousands. It's just like, but it's that kind of loving the experience. And I really, as I've got older, I really rate that. And it's kind of like valuing the experience of using tape, I'd imagine, because it's much more suited regardless of how unsexy it is. It's like people say the most sexy thing is probably the best thing to do because it's the safest or it's the quickest. It might not have much buzz to it, but it's most effective.
Right. Yeah. If you want to save photos of your kids' birthday when they were 4, that's a very different set of requirements than, oh, I want to rent access to all the music that's ever been recorded.
Yeah.
That would be Apple Music or Spotify, right?
Yeah.
But it's not specific to you. If it's specific to you, then you want something that's going to last 50 years and it's not going to cost you 2 arms and 3 legs.
Yeah.
So
that's a cool way of looking at it. That's a really cool way of looking at it. And thinking, there's loads of analogies I come up with of like thinking that kind of route of doing things. And what did you say? Did you say you had any advice for people that are looking at, I guess that kind of is advice with the trends, but anything further like that are looking, maybe they're hitting the challenge, or they're thinking, should we invest with HPC or should we invest with some other solution or some other opportunity? What would you kind of say, or what would you recommend, maybe just for investing in HPC? Because to me, it looks like a solid winner. But what would you recommend?
So what we see when we talk to our customer base is everyone's experimenting with AI and machine learning, trying to understand how they can use it, what benefit they would get. The experimental phase is, we believe, very different from production. And with an experimental, you're going to buy a DGX and then just set an engineer in front of it and a data scientist, and they're going to use it. Or maybe even just a white box computer with 2 GPUs in it until you really say, okay, I understand there's something basic here. Let's invest a little bit more and see if we can really productize it. Then you go to production. And so knowing that there's this distinction, you might do all of your experimentation in a cloud, public cloud, because they've got access to GPUs and just it's easy, right? But then once knowing that there's a difference between experimentation and production, you say, well, I don't want to spend, $100,000 a month on a cloud-based AI solution. When I go to production, I need to be prepared to have it on-prem. Maybe not, right? Depends. But that's why knowing that distinction is important. You can plan for the different phases.
Yeah, that's a great piece of advice. That's awesome. Yeah, I'm looking forward to being in person. I'm doing another interview because this is there's some real cool areas. And I like how we relate it back to situations like the car or like with new technology coming through. So Curtis Anderson, really appreciate you joining us, and really appreciate your time.
Great, thank you.
To everyone watching, I hope you've had a good time, and I'd encourage you to reach out to Curtis and to go see the awesome things that they're doing at Panasas, and find them on their socials, visit their website, which you can see on the overlay here, and get in touch, because if you're kind of mesmerized by the things I've looked at today, there'll be people that, especially when it's your business, you'll have the right solutions and the right kind of people looking at it and giving you the right answers, which is what people always want. But yeah, Curtis, really appreciate it. Everyone joining us, thank you again, and we'll see you on the next one.